All right, in this part of the notes, we are looking at making and analyzing a histogram. I do understand this is by no means one of the easiest tasks. It does involve some work. So let's go ahead and take a look at this information. We are still using the data from the very first page of the notes, which is the baby weights. So I will try to flip back and forth through this. If you guys have that copy down, perfect. If not, just when I flip back, just hit that pause button real quick so that you guys can get that information down. Okay. So first of all, it says make a histogram for the specified set of data, then analyze the graph. Make a histogram of the baby weights, label your axes appropriately, and use intervals of 0.1 kilograms for each consecutive bar. All right, so that means we are looking at the baby weights. Now, I will tell you, if we go back and look at the baby weights, okay, you can see we range from 3.3, 3.2 is our smallest, I believe, all the way up to 3.8. Right, so this is our smallest value. This is our largest value. That means that our table has to range from 3.2 to 3.8. Keep in mind, when you create a graph, right, we typically start at 0. But we can't start at 0 and go by 0.1 kilograms when we're looking to go all the way to 3.8. So what we can do is we create a break line. Okay, and I'm going to start here at the origin. This would be considered our origin. We create a break line, simply goes like this. Okay, and that indicates that there is a break from the data. So we're going to jump, obviously, from 0. So from the break line, we are going to create our measurements. Now remember, a histogram is a bar graph, so that means that each section, right, this section is worth one value, this section is worth a second value, and so on and so forth. So we're going to label each of these sections. I'm going to do this diagonally just so that it'll fit. We're going to say this is 3.2, 3.3, 3.4, 3.5, 3.6, 3.7, and 3.8. Okay, now using our data, we have to go back and count how many data values, right, would fit into our histogram. So again, we're going to be flipping back and forth here. If I go back to my data, okay, birth weight, well, how many values of 3.2 do I have? I have 1, and that appears to be the only 3.2. So I'm going to go back to my histogram. And I know that there's only one value of 3.2. Okay, now don't forget to label your axes, which I probably should have done first. This is baby weight. And over on the left, we're going to label this as the frequency. So how many times does that weight occur? And because we are looking at frequency, we can go by ones. So 1, 2, 3, 4, 5, 6, 7, 8. Okay. All right. So we said 1 for 3.2. Now let's look at 3.3. Well, 3.3, there is 1, 2, 3.3 values. Okay, so you can see where this bar is going. Then we go back and count the 3.4. So we have 1, 2, 3, 4, 3.4 values. Okay, so you get the idea of where we're going and how to create this bar graph. So what I want you guys to do, hit the pause button, okay, and create your own frequency table. Make sure you have this down. And then come back once you are finished gathering all of your data and you have finished creating your bar graph. So this is what your bar graph should look like once you have filled in your bars, right? The frequencies. Now, I like to go in and fill in each bar just because it gives it that, it gives it a nice visual and you can differentiate between the bars and the different heights they have. Do you have to do this? No, of course not. Okay, this is totally a preference if you like to shade it in or not. Okay, so now let's go ahead and look at A. Okay, for A, it says describe the shape of the distribution. Well, if we look at the shape, you can see that perfect mound up on top, right? And if you recall from the definitions, a shape that has a mound in the middle with tails at the end is called a normal distribution. Okay, so for A, this is a normal distribution. And then we can also look at this and say, is it symmetric or not, right? If I were to draw a line straight down the middle, is the data split up evenly? Well, as you can see, it certainly is. We have 1 on each side, 2, 4, and then we have our 6 split down the middle. So this would be a symmetric shape as well. Okay. Now, for B, it says by examining the histogram, determine the percent of data that are within 1 standard deviation of the mean. Now, this is where it's going to get tricky because we're going to have to use the information from up top, right? We found the mean and the standard deviation up top, and we're going to use that information to determine the percentage of data that fall between that standard deviation. So first of all, let me go ahead and copy this down. Our mean is 3.5, and remember I'm grabbing this from up here, from up top, and the standard deviation is 0.1. Okay, so this is the information we are going to use. Now, when we look at data in this manner, when we are talking about data within a standard deviation, that means that we are going to take X as our data value, and we are going to find how many data items are above 1 standard deviation and below 1 standard deviation. So that means we're taking the mean and we're adding 1 standard deviation, and we're taking the mean and we're subtracting 1 standard deviation. Okay? Now, the way we can write this out to simplify is we're going to substitute. Remember, sigma is standard deviation, x bar is our mean, and x is data. So we're looking for how many data items. Okay? All I'm going to do is substitute here. My mean was 3.5. minus the standard deviation of 0.1, less than or equal to x, less than or equal to 3.5 plus 0.1. Okay, if I simplify, 3.5 minus 0.1 gives me 3.4, less than or equal to x, less than or equal to 3.5 plus 0.1 gives me 3.6. So now we have this value here. Okay, this is a numerical value to help us determine the amount of data within that set. So if I scoot this way, right, I'm going to go ahead and draw on this so that you guys can see what we're talking about here. So we're looking for the amount of data between 3.4. So I know this bar here is 3.4. And 3.6. So we're looking at all of this data, right? This is the amount of data we are looking for. How much data is within 1 standard deviation of the mean? Well, how do we determine? We add them. We know that there's 4 data items here, 4 data items here, 6 data items up here. So it's 6 plus 4 plus 4, right? That gives us a total of 14. Well, 14 out of how many? This is where we look at the entire data set. We know that 14 out of the entire data set is the number of data within 1 standard deviation. So if you recall, or if you add them together, we can even look at that. 6 plus 4 plus 4 plus 2 plus 2 plus 1 plus 1 gives us a total of 20, which means that we have 7 out of 10 data items, which is 70%. So what does this mean? It means that 70% of our data falls within 1 standard deviation of the mean. Okay. Now, Let me see if I can go back here and erase this. Best I can. All right, now for C. C says suppose one of the baby weights is chosen at random. By examining the histogram, determine the probability that the weight is more than one standard deviation above the mean. So that means we're looking to set it up as x is greater than the mean plus one standard deviation, right? We want it to be more than. So when we substitute 3.5 plus 0.1, we know that we're looking at all data items that are greater than 3.6. Okay, so back to our graph. I'm going to split it up here. So if I look at all data that's greater than 3.6, that means I'm looking at these three little values, right? We have one that's 3.7, two that's 3.7, one that's 3.8. That means that three out of my 20 data items are greater than one standard deviation above the mean, which means that only 15% of the data falls within this category. Okay. All right, so we did two examples together. I want you guys to go ahead and try D, okay? Do the best you can. Hit the pause button and then come back and check your answer. So this is what you should be looking at for D, okay? You should have an answer of 5%. Now, the wording can be a little misleading in this problem. It does say what is the probability that the weight is more than two standard deviations below the mean. Okay, so if you set it up as a greater than problem, and I do see that happening often, okay, this is where you have to be careful and really understand what it is trying to tell you. In this case, we're looking for data that falls two standard deviations below the mean, anything less than that, right? So set it up, mean minus 2 times the standard deviation, and you get x is less than 3.3, right? Remember that x is representative of the data we are looking at, so the data has to fall more than 2 standard deviations below the mean.